Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.29. The problem statement says, a gas stream contains 18 mole% hexane and the remainder nitrogen. The stream flows to a condenser where its temperature is reduced and some of the hexane is liquefied. The hexane mole fraction in the gas stream leaving the condenser is 0.05. Liquid hexane condensate is recovered at a rate of 1.5 liters per minute. All right, let's draw our picture here. This is similar to the picture that they gave to us in the book. The only thing I've done a little different is I've broken out the mole fractions for hexane and N2. And I've also added stream numbers here for stream number 1, stream number 2, and stream number 3. I'll try and put a subscript here for stream number 1, stream number 2, and other ones for stream number 3. We know that the mole fractions, it only has 2 species, so the remainder mole fraction is just 1 minus this mole fraction, and for the same thing for nitrogen over here, it's just 1 minus this mole fraction. Part A says, what is the flow rate of the gas stream leaving the condenser in moles per minute? Hint, first calculate the molar flow rate of the condensate and note that the rates at which hexane and nitrogen enter the unit must equal the total rates at which they leave in the 2 exit streams. So the first thing I think we want to do is collect all the information that we'll need from the back of the book. Right now I see that we'll need data on hexane and potentially on nitrogen as well. We for sure will need some data on hexane here because we'll need to convert this volumetric flow rate into probably a molar flow rate because the rest of the stuff is in moles. So we'll need the density and we'll need the molar flow rate, or the molar mass. Okay, so let's grab that from the back of the book. Okay, so we've got our molar mass of hexane, we've got our molar mass of nitrogen, and we've got our density of hexane. Now, let's calculate what our mole fraction is for the nitrogen in both streams. All right, so for stream 1, our nitrogen mole fraction is 0.82, and that's because, like I said before, this is the relationship with all of the mole fractions. When you add up all the mole fractions together for a certain stream, they should equal to 1. And same thing for mass fractions. And then we do the same thing for stream number 2, and we get 0.95 for stream number 2. Now it's time for us to do our material balances on hexane and nitrogen. Alright, so here we've done our material balance for hexane. We have a certain amount of hexane going in, and then we have 2 streams where hexane is going out. So we have a minus sign, and we're getting hexane out from stream 2. That's the molar flow rate of stream 2 times the mole fraction of hexane in stream 2. And then the same thing for stream 3. We have a molar flow rate in stream 3, and then we have a mole fraction leaving stream 3. Except for that mole fraction is equal to 1 because only hexane is leaving stream 3. So then that just goes to 1, and we're just left with the molar flow rate in stream 3. Alright, so now we need to ask ourselves, what is the molar flow rate of stream 3? Well, the molar flow rate of stream 3 is something that we can try and tackle first before we try and tackle these other 2 terms of stream number 1 and stream number 2. The reason for that being we have some volumetric data that we can use on stream 3, and there's no mole fractions. So it makes stream 3 a little bit easier to work with. Alright, so we have stream 3 number of moles. That's going to equal the mass flow rate divided by the molar mass. Well, then we say, okay, well, we've just kind of traded our problems here. What's the mass flow rate? Well, they gave us volumetric data, and we know that the mass equals the volume times the density. Okay, so let's put that in. Okay, so we have the volumetric flow rate of stream 3 times the density over the molar mass of hexane, and we have data for all of these things. They gave us the volumetric flow rate. We looked up the density from the back of the book, and we also got the molar mass from the back of the book. So now we can calculate the mole flow rate of stream 3. All right, here we've got the volumetric flow rate multiplied by the density. We need to do a unit conversion to get our liters into meters cubed. And then we've got the molar mass, which is kilograms per kilomole. And then that equals to this, kilomoles per minute, and then we convert that into moles per minute because that's what the question asked us to calculate. All right, at this point we've calculated about all we can just using our hexane balance. So now let's move over to our nitrogen balance and see if we can get another equation that helps us calculate the unknowns that we have. Currently we have two unknowns in this equation. We have our mole flow rate in stream 1 and our mole flow rate in stream 2. Those are our two unknowns. So we need another equation that uses these same unknowns and that doesn't introduce any more unknowns, and we'll be able to calculate what these two unknowns are because we'll have a system of equations, two unknowns. We can solve that using linear algebra. Okay, so now we've got our nitrogen balance here. We have a certain number of moles of nitrogen going into the condenser from stream 1 and only nitrogen leaving the condenser on stream 2. There's no nitrogen in stream 3. So these two streams should be equal to each other, and sure enough, we have the same two unknowns in this equation, and we already calculated what these mole fractions are. So now we have a system of equations, two unknowns, and we can solve that with linear algebra. Alright, so I've written the two equations with the two unknowns in a form that is easy to see the two equations, two unknowns, and it's set up in such a way it would be easy to calculate what the two unknowns are. I'm not going to go into how to solve this because I think most of the viewers at this point are familiar with how to solve a system of equations, so we'll skip to the answer to this. Alright, so here we have our answer for what N1 and N2 are equal to. They should be, you can check if you entered all the numbers in correctly to see if the number of moles that they're different by is a difference of N3. And I double checked this, and that is true in this case. And now we've completely answered part A because we have the total molar flow rate of gas leaving the condenser. So that is the answer to part A. Okay, so for part B it says what percentage of hexane entering the condenser is recovered as liquid. So what is the recovery percent? Alright, the recovery percent is given by how much hexane do you recover in stream 3 versus how much hexane do you have going into the condenser. The amount of hexane you have going into the condenser is the number of moles going into the condenser multiplied by the mole fraction of hexane. And then we have a percentage because it asked for a recovery percent, and this is equal to 76.0%. That's using N3 and then the two other values that we solved for. Great, and that is it for problem number 3.29. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem solving videos. Thanks again, and I'll see you in the next video.